So we want to proceed here and determine an optimal number of cards to buy, a strategy. So let's say the person pays, he has a strategy of buying small sets to improve his chances of getting a complete set. And let's we'll say that packs of cards cost 5 cents each, but that you can buy individual cards from a dealer for a quarter. And the individual cards that you buy from a dealer, you know who's on them. That is, you can fill in the holes. You can buy random cards in the packs for 5 cents each, but then when you discover you're missing a particular player, you can go to a dealer and buy that card that you're missing for a quarter. So because the random cards are cheaper, you want to acquire as many of the unique players that way because it's less expensive. But you know you're not going to get them all. You know you'll just keep spending money, and it's unlikely you'll get a complete set. It's possible, but it's unlikely. What is the cost associated with this overall plan, the strategy? 5 cents for random cards, a quarter for the dealer cards that you know the value of, you know the player. Is there an optimal number of cards purchased that will minimize the expected cost? Well, we're going to address that. We're going to write another function, collect 2, that will simulate this, and there'll only be one argument in purchased, which is the number of cards that the person buys, the number of cards purchased. And we'll assume, as we mentioned, a random card is 5 cents. So we'll have cost.rcard, a nickel. And the cost of a card from a dealer will be a quarter, 25 cents. So cost.ncard is, or known card, if you will, is, known starts with K, ncard, whatever that is. The dealer card is a quarter. So we sample in-purchase cards with replacement from a complete set. The in-purchase cards are the ones you're buying, 1 to 586. And we compute the number of unique cards that we get out of the set. And the number we're missing, then we go off and buy from a dealer for a quarter. So we paid a nickel for the ones we sampled, and we pay a quarter for the ones that are remaining that we don't have. Is there an optimal number that we should buy, 3,000, 4,800, that will, the expected cost of the entire scenario, buying the random cards and the dealer cards, will be minimized? Can we answer that? Can we look at it? The answer is yes and yes. We can look at it and we can answer it. Okay, so here's a new function that we create to address this. And it just takes the number that we purchase. This is our sampling, the number that we're sampling from the fixed set is what this is in purchased. So the cost of the random cards, nickel, cost of the dealer card, a quarter. We're sampling, here's a complete set. This is the number we're sampling, that's the number we passed in, and we're replacing. So we've seen all this before. We determine the unique values, the length, the number, and we put that in here. And so then, but this is new, the number we're missing is the total set minus this. Those are the number missing, and those cost a quarter. So the total cost is going to be this number times a nickel plus what's left over times a quarter. So this function will compute it exactly. The only thing that will vary is this. So we can pass in different numbers here and see what this function will return. Like all functions, will just simply return the last thing executed, the last line, which is this. So the function returns the cost, the total cost. And we can then pass in different numbers of how many we're buying, and see if the cost goes up or down. Find the best point, the best number to buy. So instead of 3,000, so we need to read the function in. I always forget to do this. So we read it in.